Welcome. Today we're starting Chapter 9 on infinite series. Our section today is about sequences. You've already kind of started this where we talk about writing the terms of a sequence. So today we're really going to focus on whether a sequence converges or diverges. And then next lesson we're going to talk about monotonic and bounded sequences and properties of those. So what does it mean when we say a sequence converges? So when we say a sequence converges, what we're really meaning is that the terms approach a certain value. So we can see that like the sequence 1 over 2 to the n, where the terms are a half, a fourth, an eighth, a 16th, 1/32, so on and so forth, that eventually is going to converge to 0. The limit of those sequences is approaching 0. I may never get there, but it's still just limit. So when we talk about the formal definition, it gets a little complicated, but let's talk about what it means because I think it's good to understand. So let L be a real number, then the limit of a sequence of a sub n is L if for each epsilon greater than 0, there exists a capital M greater than 0 such that the absolute value or the difference between my sequence, my nth term, and the limit is less than epsilon whenever my term number is greater than capital M, okay? So if that limit exists, then we converge. If it doesn't exist, then it diverges. Okay, so let's take a look at what this means. And so I think visually can help us the most. So epsilon is any number you want it to be, okay? So epsilon can be anything. And usually what we think about is something really tiny, okay? So tiny, 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 tiny. And so for any tiny number you pick, no matter how tiny you get, we can always go far enough in my sequence, which would be M, such that the terms are always within epsilon units of my limit, okay? So all of these term numbers here, I'm not always within, I can be a little bit, but because of this term, so yeah, these two terms over here, let's say my like 6th and 7th term or whatever, those are within epsilon units, but I still have these two terms out here that aren't. So not all of them are within epsilon units of my limit, but once I get past M, all of these are within epsilon units of my limit. So for every epsilon you pick, no matter how small, if there is a term number that once you go past it, then you're always within epsilon units of your limit, then that's what we say for it to converge, okay? So I want to just get infinitely close is all it's basically saying, okay? All right, so limit of a sequence. So the limit of a sequence is basically if I just turn my formula for my nth term into a function and that limit exists, then we say the limit of the sequence exists. Properties of limit of sequences, they work exactly how you think they do. So if I have two sequences, a sub n and b sub n, and they have limits L and K respectively, then we can add, subtract, multiply, divide those. And we can also have a scalar multiplier. So if I multiply every term of my sequence by a scalar, I can go ahead and multiply the limit of my sequence by that scalar as well to get the new limit. Okay, so everything works exactly how you think it does. No tricks. It's fantastic. Okay, let's talk about some examples here. So we're starting with example 3 because example 1 and 2 in the book were ones that were very similar to ones you did on the worksheet for the sequences review. So we don't need to go over those. So our first sequence here that we need to figure out if it converges or diverges is 3 plus negative 1 to the n. So my first term here would be 3 plus negative 1, so that's 2. My second term would be 3 plus negative 1 squared, so 4. Third term, 3 plus negative 1 cubed, so 2. So my sequence here is alternating between 4 and 2, okay? And therefore, the limit does not exist, so then I am going to say this diverges, okay? So limit does not exist, so my sequence a sub n diverges. All right, my next sequence is n over 1 minus 2 to the n. And so for this one, we are going to look at it and figure out if it's going to converge or diverge. So what I'm going to do, if I'm going to look at the limit as n approaches infinity of n over 1 minus 2 to the n, I'm going to go ahead and multiply the top by 1 over n, just so I don't have to worry about having infinity in both the numerator and the denominator. So now I get the limit as n approaches infinity of 1 over 1 to the n plus minus 2. And so then here we see that this term goes to 0. So then my limit is just going to be negative 1/2. So this one we would say converges to negative 1/2. And what is converging? My sequence b sub n. All right, let's talk about a few other things. Oh, we got another example. Using L'Hopital's rule to determine if a sequence converges. Okay, so if I have the limit as n approaches infinity of n squared over 2 to the n minus 1. Well, right now I have infinity over infinity, so I'm going to go ahead and take the derivative of the numerator and the denominator for L'Hopital's rule. So I get 2n over natural log of 2 times 2 to the n, which is still infinity over infinity. So I'm going to take the derivative again. So now I have the limit as n approaches infinity of 2 over natural log of 2 times natural log of 2, so natural log of 2 squared times 2 to the n. And here I see that this term is going to 0, so to infinity. And so since that is going to infinity on the denominator, I know the whole limit is approaching 0, so I would say this converges to 0. Great. Next, the squeeze theorem. This is one of my favorite theorems. So this says if I have two sequences, a sub n and b sub n, and I know they have the same limit L, and then I know that there exists some integer n such that whenever I am greater than that, okay, so whenever I'm beyond a certain point, kind of like our definition of the limit in the first place, so once I'm past a certain term number, the sequence I'm interested in, c sub n, is always sandwiched between or squeezed between a sub n and b sub n. Then I know that the limit of my sequence, c sub n, also has to be L because both a and b have the same limit and I'm always between them, okay? So let's take a look at the sequence c sub n, which is negative 1 to the n times 1 over n factorial. Okay, so let's remind ourselves what n factorial is. So n factorial, remember, is 1 times 2 times 3 times 4 times 5 times ... times n. And then I'm going to compare this to 2 to the n. And 2 to the n is 2 times 2 times 2 times 2 times 2 ... Okay? And so if I look at these, I can always think about, well, when is it going to be bigger, right? So if I look at these and we think about n factorial, I can think about this as 24, and then, right, so if I just group these first four terms together, 24 times 5 times 6 times 7 times ... times n, okay? And then if I group the first four together of this one, I'm going to have 16. So 16 times 2 times 2 times 2, okay? So we have that 2 to the n is going to be less than n factorial when, okay, for all n greater than or equal to 4. Okay, so before that it's not, right? So before 4, n factorial is going to be actually less. But once I get past that fourth term, so that once I add the 4 and the 2 here, that's officially when n factorial is greater than 2 to the n. Okay, why is this helpful? Well, this is helpful because I can now sandwich my my sequence between 1 over 2 to the n. So essentially what I have here is I can say, oh, well, since I know this is true, then the reciprocals is going to be the opposite, right? So then I can say 1 over n factorial is less than 1 over 2 to the n, okay? And then I can also sandwich between the negative, okay? So then if I add that negative 1 to the n, the alternating piece, I know all the positives will be less than, well, and the negatives will be less than 1 over 2 to the n. And I can also do the top, or the lower bound, as negative 1 over 2 to the n. Okay, we've already talked about how 2 to the n approaches 0. So then we can say, hey, since the limit of both negative 1 over 2 to the n and positive 1 over 2 to the n are 0, then the limit of this alternating 1 over n factorial must also be 0. Okay, so the limit as n approaches infinity of negative 1 over 2 to the n equals 0, which is the same as the limit as n approaches infinity. Oh, we have to put it in here. For all n greater than or equal to 4. If you haven't seen this symbol before, this symbol right here means for all, okay? Okay, so then we have this 1 over 2 to the n. So we know both of these approach 0. Thus, by the squeeze theorem, we know that negative 1 over n times 1 over n factorial also approaches 0. Great. Okay. And here's a little visual for that. So you can kind of see that we have our function is the squiggly line in the middle, okay? And at first it's less than negative 1 to the 2n and greater than positive 1 to the 2n, but eventually it calms down and it starts oscillating between those two, right? So here is 1, 2, 3, 4. So right here is the fourth term, and after that it's always between the two, right? So it oscillates between those two functions, okay? And so once I'm 4 and beyond, since I'm between those two and both of them are approaching 0, one from the top, one from the bottom, then my function that is bouncing between them will also approach 0. Okay, absolute value theorem says for a sequence a sub n, if we know that the limit of the absolute values of the terms equals 0, then the limit of the terms themselves equals 0. And you can basically think about this as using the squeeze theorem. Okay, so I know that the my terms, whether they're positive or negative, are going to be sandwiched between the absolute value of a sub n and the opposite of the absolute value of a sub n. And so since this goes to 0, then this also goes to 0, which means my terms must go to 0, okay? So that's just using the squeeze theorem. So the absolute value theorem is just a specific case of the squeeze theorem. Okay, so go ahead and try your homework, and we'll go over all of this in class, all of your questions in class next time.